Okay, let's record. Okay, so today we are going to uncover the hydrogen atom. So today is a big calculation day. And in some sense, we're going to be deriving probably the most important equation in quantum mechanics, which is the Bohr equation, which is an equation from which one can get all of the energy eigenstates of hydrogen. In some sense, this is one of the very few real-life calculations we can actually do. There aren't that many quantum mechanical systems we can solve in this way that are real-world systems. On a logistical note, I assume people will be watching this asynchronously. The papers are due today. I know it says 5 o'clock, but it's okay if it's later. For those of you that have sent me topics, we've discussed everything, so I think you should be good to go. I will be sticking around after. We only have a few people today. Any of you want to discuss anything, I'll be sticking. I was going to stick around to discuss people's papers, but I guess everyone is okay. If any of you want to, I'll be here. Okay, so let's get started. Before, any questions, quick questions about last time when we went over the harmonic oscillator? Okay, let's begin. Okay, so the first thing we're going to have to do for the hydrogen atom is we're going to have to rewrite, and I have notes, I wrote up notes today because the calculation is pretty long, and I'll give you fair warning. There's a lot of algebra that I skip. There's a lot of steps that I've done, but I mean, I've worked it out. So this is sort of the smooth picture. For those of you at home that are going to try this calculation on your own, you shouldn't work it out in such a smooth way. You should work out all the gory details. But even with this sort of smooth picture, it's still a pretty hard calculation. But it's a very important one. In physics, we do these kinds of calculations a lot. So it's important you understand sort of the mathematical techniques. And I'll explain them as we go along, but it's a little terse. Much more different than the harmonic oscillator, which was simply an algebraic explanation. Okay, so before we begin, we're going to need a 3D Schrodinger equation, which we've discussed before, so I'll just give you a reminder on how that works. So here's our Schrodinger equation. Okay, that's pretty straightforward. And if I have some Hamiltonian, right, I can rewrite this in the following way. Well, this should be, well, right, it's fine. I can write the Hamiltonian in this way as well, which we've seen before, right? Because the energy can also be written as p squared over 2m plus some potential. And of course, now in quantum mechanics, these momentums are promoted to operators, which for us is pretty standard at this point. Okay, all pretty standard stuff. We have our operators, and in 3 dimensions, I can recast my momentum operator in 3D as h bar over I times nabla. Okay, so this is sort of our 3D picture now. We have our momentum operators in 3 directions, and we can sort of recast them into this sort of streamlined format. Using that, our Schrodinger equation in 3 dimensions is pretty straightforward. It's just IH bar d psi dt equals minus h bar squared over 2m nabla squared psi plus some potential b psi. Now nabla squared, this is called the Laplacian. Okay, so we have a Laplacian operator now in our 3D Schrodinger equation. Okay, and the Laplacian is defined in the following way, which, I mean, we've seen all of this. It's just to give you a reminder. It's just the second partial derivative in each direction. Okay. Okay, so we have our 3D picture. It's sort of spelled out now. And now we can start defining some more of our quantum mechanical algorithm in 3 dimensions. So first of all, now our integral of psi squared, which is the probability density, is now a 3-dimensional integral. And that's going to equal 1, right? But now my integration measure has changed to reflect that it's 3-dimensional. So d3r is just dx, dy, dz. That's my integration measure. Okay. And psi now goes to 3 dimensions as well. It's a function of this vector r, which is 3-dimensional. So I can define this vector r as a 3-dimensional vector. X, Y, Z. Okay. Which is straightforward from your freshman physics classes or high school physics classes. Right, and now all of our solutions from before just get translated. So our general solution for the wave function now comes in multiples of n, as we've seen, ENT over h bar, except now it's a function of 3 dimensions. It's a function of r. And my time-independent Schrodinger equation also kind of takes the same form with my Laplacian. Okay, pretty straightforward. I'm just sort of translating what I have above, and I can have different multiples of my wave function and different multiples of the energy. Okay, so this is time independent now, right? Where this nabla represents total derivatives. And now I can rewrite any general solution, just to really hammer this home, psi r and t as some sum over Fourier coefficients, e to the minus I, e, n, t over h bar. So again, this is a Fourier series. It's a general solution. These are my Fourier coefficients, and I'm summing over all of them. And I'm getting various wave functions and energy eigenstates. Okay, so this should all be pretty easy to digest, pretty straightforward, and it's not too complicated, I hope. So now we're going to have to adopt a special coordinate system to talk about a hydrogen atom. We're going to have to adopt spherical coordinates. So here, my integration measure, the dimensions, so that I'm integrating over are x, y, and z. Okay, d3r. This tells me the dimensions of my system. Now in physics, the dimensions of a system are called a basis, right? So a basis is simply kind of the geometry we're working in. Now, I can have all kinds of bases, right? I could have, this is a Cartesian basis, x, y, and z are the spatial components. In spherical coordinates, we are changing the basis. So now x, y, and z are not going to be our spatial parameters. Now our spatial parameters will be 3 things, r, theta, and phi. And I'm going to explain what those mean in our basis. Okay, so r is the radius of the sphere, right? So we're going to need this sort of angular description to describe the physics of hydrogen. Theta is going to be the angle coming down around the sphere this way. So we call it the polar angle. And then there's only one more degree of freedom in the system, and that's phi. Phi is going to be going around the sphere this way. That's the azimuthal angle. So those are our 3 degrees of freedom. Degree of freedom just means dimension. Those are our 3 degrees of freedom in spherical coordinates, or in the spherical basis. So now let's rewrite our Schrodinger equation and our Laplacian in spherical coordinates. Okay, so now my Laplacian becomes this. 1 over r squared del r, r squared del r, plus 1 over r squared sine theta d theta sine theta d theta plus 1 over r squared sine squared theta d2 d phi squared. Okay, so this is my spherical Laplacian. So this is just the analog of the Cartesian coordinate Laplacian, except now I have a few more basis components, which you could work out and see how that all works, which you will in a math class. And now my Schrodinger equation becomes this. Now I'm just going to plug in that Laplacian, right? So this is my Schrodinger equation now. d/dr r squared del r plus 1 over r squared sine theta d theta theta d theta d2 d phi squared. Right, so now I've just input, I have my minus h bar squared over 2m plus some potential plus b of psi equals e psi. Okay, so now my Schrodinger equation looks different because I'm in a different basis. Now, obviously, the physics doesn't care about your basis, right? You could be in a Cartesian basis or a spherical basis. The physics doesn't care about your basis. It's just a matter of what basis makes the physics easier to do, right? If I give you some kind of problem, which we'll see with angular components, right? Angular being theta and phi components, it would be tough to do that problem in Cartesian coordinates, right? How would you even define an angle? Okay. So now we're going to do the technique that we used when we were deriving the time-independent Schrodinger equation, right? So this is, I told you this technique is going to come back over and over again. We are going to look for separable solutions and separate this differential equation into various variables. So what I'm going to do, now I have psi. Psi is a function of r, theta, and phi. And now I'm going to separate it into two functions, just like we did when we derived the time-independent Schrodinger equation. One function of the radial part, r, and one function of the angular part, theta and phi. Okay. Okay, so now obviously this is going to be reflected by the fact that I have two functions. So now let's rewrite the Schrodinger equation. Now what's going to happen is all of my psi's are going to change, right? And all of the functions here are going to change, right? So now this becomes minus h4. This is exactly what we did with deriving the time-independent Schrodinger equation. Y over r squared d/dr. Now this is a total derivative, right? Because I only have one function that depends on r. R squared capital R dr plus capital R over r squared sine theta. Still partial derivatives for the angular part because I have 2 degrees of freedom I have to worry about. Sine theta d bar d theta. Y squared plus V R Y equals E R Y. Okay, so I just multiplied my whole equation really by R and Y because now I'm separating this equation as being dependent on two functions, which is exactly what we did deriving the time-independent Schrodinger equation, except as you recall, we only had two variables, 2 degrees of freedom in the time-independent Schrodinger equation, and that was x and t. Now we have 3 variables, r, theta, and phi. So this is going to be a little more complicated. We have one more function that we need to separate even further, probably, but we'll see. Okay, let's draw a quick sketch of how spherical coordinates looks, because most of you, probably all of you, have never seen this. So I have z direction, y direction, x direction. And in the spherical basis, I should make this picture bigger. And please, you two, feel free to stop me with questions. I don't want to keep talking at an empty screen for the next hour. I have x, I have z, I have y. Okay, and let's draw some vector in this basis. We'll call it p. Okay, and I have my angle coming down, which is theta, right? I have my angle, and we can draw projections of this vector going down, which I'm sure you've all seen, right? Of the components, right? We can draw projections from these components. Okay, I have my angle going around, phi, okay. So now I have 3 components, and in this basis, I have 3 basis vectors, r hat, theta hat, sorry, this should be phi hat, and theta hat. Okay, so you can think of this as some sphere now, right? It should be coming off the board. And I have 3 degrees of freedom and 3 unit vectors, or basis vectors. So now let's take this equation that we just wrote down, and we're going to divide by yr, okay? And we're going to multiply by minus 2m r squared over h bar. So let's call this equation star, okay? So let's take star, okay? And we're going to divide. I'm going to write down my algebra because I'm not going to do it all by hand today. We have too much to get through. Usually I do. So in case you want to replicate it, and then we multiply by minus 2mr over h bar, and when you do that, you get this, this is similar to what we did for the time-independent equation. You get 1 over r dr r squared dr minus 2m r squared h bar v of r minus v plus 1 over y 1 over sine theta d theta sine theta dy d theta plus 1 over sine squared theta d2y d phi squared equals 0. Okay, so I just did an algebraic step, and I'm starting to simplify my equation. Okay, so now we're going to use another technique that we've done in the past. We can observe this and see that the first term depends only on r, which is good, which is really good now. And the second term depends only on theta and phi. So in effect, the first term only depends on r, capital R, that function, and the second term only depends on capital Y. So now we can split these up into 2 separate equations that are dependent and equal to some same constant, okay? Which is exactly what we did for the time independent, where we took both of our separated equations, right? We separated the partial differential equation into 2 impartial ones, right? And we set the time equation equal to an energy, and we set the position equation to an energy. Well, we're going to do the same thing here. So let's do that. And let's define a constant now. So we've done the task. We have simplified our problem quite well. Now it's simply a matter of setting them equal to constants. So let's take our radial part that we just got, 1 over r ddr r squared dr minus 2mr squared over h bar squared v of r minus e. And I'm going to set it equal to this thing, L times L plus 1. L is just some constant number, some integer, and you'll see why I'm doing this. It's really, really suggestive of something, but we're not there yet, so don't worry too. It's not an angular momentum. And then we have a 1 over y, 1 over sine theta, d theta, sine theta, y d theta, plus 1 over sine squared theta, d2y, d phi squared. Okay, again, I have done this for a very particular reason in this calculation. So now we really have two different equations we need to solve, the angular equation and the radial equation. So let's try and solve the angular equation first. So I'll call the angular equation alpha, and I'll call the radial equation beta. Okay, and I'll just say this here. So this is the angular. And this is the radial. Okay, so let's look at alpha first, and let's see what we can get. Okay, so the first thing I'm going to do is I'm going to multiply by y sine squared theta. Okay, so that's the first thing I'm going to do. So when you do that, you get this. Sine theta, del theta. And please check my algebra as you guys do this, because it might be wrong. dy d theta is d2y phi squared equals minus L plus 1 sine squared theta y. Okay, pretty straightforward. And again, we're going to use separation of variables, right? Because now I have 2 degrees of freedom here. I have theta and I have phi. Okay, so again, we're going to do separation of variables. So we take our y of theta and phi, right? And we separate it into 2 functions. We'll call this O of theta and var phi of phi. Okay, this is a var phi. So we have our new separated equation. Okay, so now we're going to do the same game, which I told you we'd have to do. So I'm going to separate this thing and divide it by O var phi. Okay, so I'm going to separate it and then divide, which is exactly what we've been doing over and over again, by O var phi. Okay, so let's do it. What do we get? We get this long thing. This is why I use notes today, because it would be too many things to calculate and not enough time. 1 over O sine theta d theta sine theta. Now we just have total derivatives, the O d theta, because now we've finished our separation. Okay, plus 1 over var phi between var phi phi squared equals 0. Okay, now we're in business because we can do this again. Now we have 2 equations. We have one equation which only depends on O and theta, and we have one equation that only depends on var phi and phi. So now we can separate them into 2 separate differential equations and set them equal to constants. It's literally the same game over and over. And guys, why did I need this minus sign here and a plus sign here? The reason I needed a minus sign here is because I'm moving this one part over, right? And then I'm setting them equal to each other. That's really why I can do it this way. Does that make sense? Okay, right, exactly. So basically I have a theta equation here and I have a phi equation here, right? I'm saying that now I have the dependencies separated, right? And let's call the theta part rho. Okay, so this is the theta part, we'll call it rho, and we'll call the phi part sigma. And what I'm doing is I have phi plus sigma equals 0, right? And I'm saying now I've gotten all the dependencies sorted out. So now I can just set rho equal to minus sigma, right? Moving this over. And now I can separate them. I can set them equal to the same constant, right? Because this is equal to 0. I can make this any constant I want, right? Except this is going to have a minus sign, right? Because I've moved it over. So I did the same thing here. I had an L plus 1. You'll see why I chose that. I could have chose any constant I wanted. And I needed that minus sign because I chose to move the angular part over. Okay, very important to know how to do this calculation. Okay. Okay, excellent. So now I'm going to do the same thing. So let's do that. Let's separate it. So I have my 1 over O sine theta d theta sine theta the OD theta plus L plus 1 sine squared theta, and I'm going to set this equal to m squared, some mass, okay, which you'll see why. And my phi equation is just 1 over var phi d2 var phi d phi squared equals minus m squared, okay? So that's why I have these minus signs creeping around. Okay, great. So let's solve the phi equation. Solving the phi equation is super straightforward. So let's solve phi equation. And this was just going to be some plane wave solution, right? So I have d2 var phi d phi squared equals minus m squared phi. Okay. And I have my solution, which is my typical plane wave solution, var phi of phi equals e to the I m phi. Okay. That's my typical plane wave solution for these kinds of differential equations. And obviously, because this is periodic, this is an angle now, if I do var phi of phi plus 2 pi, I'm going to get back var phi of phi, right? Because if I move up by 1 period, 2 pi, right, on the circle, it's just coming back to the same spot. Okay. Okay, so I can literally rewrite this thing, and I should erase everything. Okay, I can literally rewrite this thing, because now if I take my phi and I add 2 pi to the angle, I'm just going to get back the same point, because that's how the periodicity works, right? So now I can rewrite my solutions like this. E to the im phi plus 2 pi equals e to the im phi equals e to the 2 pi im, all equal 1, right? They're all going to bring me back to the same point, right? And therefore, m could be any of these integer values. M could be 0, it could be plus or minus 1, or it could be plus or minus 2, so on and so forth. So it takes all these integer values because of the periodicity of my angle, phi. Okay, so solving the phi equation was really simple. It's a straightforward differential equation, and it gives you back plane wave solutions. And we've exploited the periodicity of phi by adding any 2 pi to it to get back the same angle, and we can write these identities and obtain integer values for n. Okay, now let's solve the theta equation, which is a bit more complicated. So we're done with the phi equation. We've solved that story. It was pretty straightforward. We've canceled out 1 degree of freedom. So now, if we have the theta equation, it's a bit more complicated. How should we solve this thing? Let's take a look at it. I'm going to rewrite it at the top. I seem to have missed a 1 over theta. Let me just make sure I'm okay here. Okay, it's fine. Okay, so we're going to multiply this thing by theta. We're going to multiply this thing by O. So let's multiply. So let me rewrite this up top, just so it's clear. So I have 1 over O sine theta d theta sine theta d theta. Sorry, these lawnmowers are really loud. Okay, so I've just rewritten that up top, and now we're going to work on the theta equation. So the phi equation's done. We've done our separation of variables again, and all I'm going to do is I'm going to multiply this thing by O. Yeah, so let's multiply by O. Not to be confused with the step function, and I just get this thing. This should be a squared. Okay, and I'm going to move the m squared over. All multiplied by O equals 0. Okay, so now I have my theta equation recasted, just with some simple manipulations. And the solution to this thing, this is going to be the first of many that we're going to see today, goes like this. So theta, O of theta, which is the solution to this thing, is equal to some constant A, P, L, M. This is a special function we're about to define, cosine theta. And these special functions are going to keep popping up now. So ML. It doesn't matter, but that's how they conventionally define it. PML is your first special function. It's called a Legendre polynomial. These are going to be very important because they're going to help us solve the hydrogen atom, these special functions. It's a Legendre polynomial, and it's defined in the following way. PML of x is equal to 1 minus x squared, m over 2, d dx of m, PL of x. Okay, so let's see how this works. Okay, we define them in a very particular way. Okay, we define them in a different way. We take the Legendre polynomial and define them by the Rodriguez formula. So define Legendre, and we're going to compute some of these to show you how it works, by Rodriguez formula. So I define this thing PL of x equal to 1 over 2 to the L times L factorial d dx to the L, x squared minus 1 L. Okay, so now I have some special functions. This is the solution to the theta equation. It involves this special function, this combination. And you can start to see why I chose m and L. M and L are the integers that I can plug into this thing. So let's compute some of these. And I'll rewrite the formulas up top. This way it's not so confusing. Okay, so the radial equation, we need special functions. And you should try and plug in some of these and see their solutions. We have our Legendre polynomial. Very, very important to know this stuff because it comes up, these special functions come up so many times as solutions to things. Okay, we can define it with the, so I'm just gonna bullet point these. We can define it with the Rodriguez formula. We can, I mean, it might not be so practical to use it that way, right? And that gives us this equation. Okay, so let's compute some of these things, just so you can see how they work. Also, can someone give, no, I will, just give me a second, I want to check the time. Make sure I'm not running low. Okay, it's 10:11. I have plenty of time, but we're not going to get a break today, guys, because there's a lot to do still. Okay, so let's compute some of these. So let's do the Rodriguez. So P0 of x, right? So L can be any integer. So the Rodriguez, so P0 of x equals what? So if this is 0, 2 to the 0 is 1, right? 2 factorial is 1, right? D dx, you know, and you can plug the whole thing in. If 0 is nothing, okay? 0 squared is 0, you get a minus 1, and to the 0, let me just work this out. Yes, you get 1. So when you work out P0 of x, you'll get 1. Just plug in 0 everywhere you've seen L. Okay? P1 of x equals 1/2 d dx, x squared minus 1 equals x. P2 of x equals 1 over 4 times 2, right? Because 2 squared is 2, 2 factorial is 2, right? D dx squared, I'm plugging that in for L. And then x squared minus, this should be a 1. Sorry. X squared minus 1 squared, right? Anywhere you've seen L, just plug in the integer that you chose. That should yield a 1/2 3x squared minus 1. Okay, and now some Legendre polynomials. P11 equals sine theta. P01 equals cosine theta. P12 equals 3 sine theta. You know, and you should compute some of these. I'll just, 3 sine theta cosine theta, sorry. Okay. P22 equals 3 sine, I'm just picking out, I just computed random ones. You can check to see if they're right. 1/2 5 cosine cube theta minus 3 cosine theta, and so on and so forth, okay? So these have solved our theta equation. So we've solved the theta equation. We needed some more machinery, Legendre and Rodriguez polynomials. Okay, let's rewrite our integration measure in spherical coordinates. So now d3r becomes r squared sine theta dr d theta d phi. And our integral for our probability density is just this thing now. Right? And I can rewrite this as the integral of r squared, capital R squared dr, right? Because I've split up this integral. I've split up the r part for the capital R function that only has an r dependence, and it becomes a double integral with my angular parts in the other, d theta, d phi. Okay. Okay, so basically we can recast this whole piece. We can recast this into an angular part, theta and phi, which is obviously y is dependent on theta and phi, and capital R is dependent only on r. Okay, and obviously this whole thing equals 1. Shouldn't forget that. Okay, anyone have any questions? Mansoor and REM, are you guys okay?
Yeah.
So far? Yes?
Yeah.
Okay. Okay, I mean, we haven't done anything too complicated yet, so. Okay, now we can normalize these things separately, right? Now we don't have to treat them as two independent things. So let's write down how we would and remember, all normalizing means, when I say normalize, I mean that the integral of the probability density, r squared or capital Y squared, should equal 1. That's all I mean. If it doesn't equal 1, then it's not normalized. So we have our r part. This comes from our new integration measure. This is integrated from 0 to infinity. Now we have two integrals for the y part, right? Because we have a theta part and a phi part. Again, it has to equal 1. The theta part, the phi part goes from 0 to 2 pi, right? That brings you all around the sphere. But the theta part actually goes from 0 to pi, which is weird because actually if you look into it in radians, if you go from 0 to 2 pi, that would take you in this direction twice. So not to confuse you where I get these bounds. And you'll see these are triple integrals, right? Because now you have 3 degrees of freedom to worry about. Not very complicated, you're just adding new things. So now we have angular wave functions, right? We have y of L and M, right? Okay, so the angular wave functions now, the normalized angular wave functions are called spherical harmonics. They're extremely, extremely important. Okay, so now we have our spherical harmonics. You guys are getting like also a Calc 3 lesson here as well. Okay, so let's write them down. Now we have two integers. The first one is equal to 1 over 4 pi to the 1/2. And I'll write down a formula for you. If I plus or minus 2, I get 15 over 32 pi to the 1/2 sine squared theta e to the plus or minus 2 I phi. And I'll write down one more. I have 5 over 16 pi to the 1/2 3 cosine squared theta minus 1. Okay, so now I have 3. I could keep writing them. And the equation now for my spherical, or my normalized wave functions is y ml of theta and phi. This is a first important formula, equals some constant, we'll call it epsilon. I mean, that I haven't written that out here at all. Times 2L plus 1 over 4 pi times L minus M times L plus M. Now you can see why I use these L's and M's, because they're just coming from solutions to these things. E to the I M phi times our Legendre, corresponding Legendre polynomial. Oh shoot, cosine theta. Okay. This is our spherical harmonics formula. Okay. Oh, and I'll define epsilon for you. So epsilon equals -1 to the m, right? When m is greater than or equal to 0. So I've defined this sort of normalization constant. And epsilon equals 1 when m is less than or equal to 0. So depending on what integer you choose for 1, that will tell you what value epsilon takes on. Is all of this pretty straightforward? It's not too complicated, right?
It's not too complicated.
Sorry?
It's not too complicated.
Exactly, exactly. We're just sort of rejiggering things, right? We're sort of adding some pieces to it. It's not, we're not doing anything really fancy yet. And you should check that the Legendre polynomials are solutions, right? You should just pick a Legendre polynomial, plug it in, and see if it solves the equation or not. That's important to really check. And obviously, our wave functions, y, m, l, are orthogonal to one another. So we can write that, which we've done with normal wave functions, right? So if we had normal wave functions, we've written out that if we had some psi m, psi l, to say they're orthogonal just means that this equals the Kronecker delta, right? That if they're equal to one another, you get 1. If they're not, the integral cancels out. So similarly, our wave functions, our spherical harmonics are orthogonal. So how can I write that out? Again, I'm going to have two integrals, one from 0 to 2 pi and one from 0 to pi, right, for my theta and my phi and theta degrees of freedom. And now I just have y, m, l, theta, phi, star, right, because you always take the complex conjugate of 1 when you're squaring it, times some y, m prime, l prime, theta, phi. And then we have my integration measure, sine theta, d theta, d phi, which I defined. And again, now I just get two Kronecker deltas, d, l, l prime, Kronecker delta, m, m prime. Okay, so now they're orthogonal as well. So this is why it's so important that we built our mathematical foundation early on, because now it's not, this looks really complicated and daunting, but it's really not. It's just sort of reformulating some things. You might want to look into where these bounds come from in a calculus textbook or something, but it's straightforward. But now, you know, you should be wondering something, which is sort of crucial. Just want to check the time. Okay, I have plenty of time. You should be wondering something which is really interesting, and that is, last time, actually the first time we looked at dynamics of the Schrodinger equation, I said that basically all it comes down to, all of the dynamics, all of it comes down to solving the potential, right? That the potential was the most important thing. And so far in the 30 minutes we've been solving the radial and the angular equation for theta and phi separately, I haven't even mentioned a potential. Why? Because the potential was in the radial part, right? The potential is in the radial part. So obviously the radial equation is going to be the most important, and the radial equation is really going to tell us the dynamics. So we've sort of solved the angular part, but now we need to focus on the big stuff, which is the radial part. So let's write down our radial equation. Because the radial equation has the potential. It's going to tell us about the system. So I've saved the best for last, actually. This is actually going to be the most difficult thing now. Minus 2mr, which is what we've derived, times our potential, minus e times capital R. And we set it equal to this weird constant thing. Okay, and remember, capital R is just that function that depends on the radius. Guess what we're going to do? We're going to, oh no, we're not going to separate any. We can't separate anything now, but we're going to impose a change of variables. So let u equal little r times capital R of R. Okay, From this, it follows that capital R equals U over R, right? And that dr equals this thing, du dr should be times du dr minus U divided by R squared. Okay? Just imposing this simple algebraic change of variables, my radial equation now looks like this. ddr r squared d capital R dr equals r d2u dr squared. Okay? And now I have my Hamiltonian, and if I input this thing into my Schrodinger equation, the Schrodinger equation now becomes minus h bar squared over 2m. Well, the radial Schrodinger equation, right? d2u dr squared plus v plus h bar squared over 2m times L over L plus 1 over R squared, U equals P little u. Okay? So all I've done here is some algebra to reformulate my Schrodinger equation for a very specific reason. And now it's time to talk about a hydrogen atom. Now we've done all the legwork, sort of 1 hour of just pure algebra and manipulation. And now we can talk about the hydrogen atom, because all of our physics for the hydrogen, I mean, yeah, there's an angular part, right, is going to be coming from this radial equation. So let's draw it out. So what is a hydrogen atom? So if I have some proton in the atom, in the atomic, okay, it's a very heavy thing. And it's so heavy, the proton is so heavy versus the electron that we say it's just in place. So the proton is in place, right? So this is my proton. We'll call it P. And in orbit around the proton, or we'll call this E plus, right? Because I know we'll call it P. I don't want to confuse people. Okay, and we'll draw some vector R. And now we have our electron spinning around it, E minus, moving around it, right? Now you can see why spherical coordinates is so nice. Okay, so really in the hydrogen atom, we have a heavy motionless proton, and we have an electron circling around it, much lighter electron. That's why it circles around it. So in your homework for this week, there's a problem set. I came up with a problem called, are we an electron? So I want you to solve a lot of these equations, but treating the solar system as a hydrogen atom and seeing what numbers you would get using the mass of the sun and the mass of the earth and so on. Okay, so now let's dig into the radial equation. So first of all, I want to define my potential, this piece, as V effective, VEF as V plus h bar squared over 2m, L plus 1 over R squared. Okay, so I'm just defining my potential now. And this term, h bar squared over 2m times L plus 1 over R squared, is called the centrifugal term. And you may have heard of what a centrifugal force is. A centrifugal force is an outward force, right? It's a force that pushes out. The reason we call this the centrifugal term is because it's the term that's responsible for sort of throwing the particle outward from the origin, right? It's the force that's responsible for throwing this electron away from the proton, okay? And you can kind of see this, right? Because it has this inverse square in it, 1 over R squared, right? It has a 1 over R squared term. So it kind of works like Coulomb's law or FG, GM1M2 over R squared, where it's, you know, it's kind of throwing that thing out. There's some repulsive force there, balancing the attraction. And please stop me if you have questions. Okay, so let's solve the hydrogen atom. Let's do it. This is the big triumph now of quantum mechanics that we're about to do. And now the math is going to get a little complicated. Okay, we have the effective, we have a centrifugal term. So from Coulomb's law, the potential for our system is minus E squared over 4 pi epsilon naught 1 over r. For epsilon naught is a constant. You guys have probably seen this from Coulomb's law. Coulomb's law is K Q1 Q2 over r squared. K is a constant, right? A Q1 Q2 are the charge. Epsilon naught is the permittivity of free space. That's the constant, right? So these are just numbers, and this is our potential. So now plugging this in, our radial equation becomes minus h bar squared over 2m d2u over dr squared plus minus, now I'm plugging in my Coulomb potential, 4 pi epsilon naught 1 over r, right? Plus my centrifugal term, h bar squared over 2m L plus 1 over r squared u equals E u. So I've just plugged in the potential and I have my centrifugal term. Nothing complicated there. And now we want to solve. So now here's the goal now for hydrogen. We want to solve u of r, right, the radial function, and determine the electron energies, or energy eigenstates. Electron energy eigenstates. E. Okay, now the goal has been set. Oh, but unfortunately, we're going to need some nice mathematical trickery to do this. And obviously, I should mention this technicality. When we get discrete energy values, that really means that we're solving for bound states. There are states of the hydrogen atom where you could get continuous energies if you do something called a perturbation. But we're not going to look at that now. We're going to look at just bound states, which is what Bohr did when he solved this. And so Bohr did this without quantum mechanics, by the way. I don't know how he did it. He used some crazy classical mechanics argument. So I'm going to do some more definitions. Let kappa equal minus 2me over h bar. I'm going to clean up this equation first. Okay, so kappa is that thing. Now we divide by E. And we get what? So I'm taking this equation, I'm substituting in kappa, and I'm dividing by E. And when you do that, you get this thing. 1 over kappa. This is why I use notes, so I don't have to work out all of this algebra that I did. d2u dr squared equals 1 minus me squared over 2 pi epsilon naught h bar squared k 1 over kr plus L plus 1 r squared u. Okay, so I've rewritten my radial equation, just substituting in kappa and dividing by capital E. Okay, we're going to do even more substitutions. So let's define rho. Let rho equal kappa little r, and let rho naught equal me squared over 2 pi epsilon naught h bar squared k, or kappa. Yeah, kappa. Okay, and you can see I have that thing here. That's why I kind of did that. And so now my equation becomes d2u d rho squared, right? Now it's dependent on rho because rho is now defined by kappa and r, equals 1 minus rho naught over rho plus L times L plus 1 over rho squared u. Okay, so all I've done here is just done some nifty substitutions to simplify my problem. Any questions so far? No questions? We're all good? Okay. Okay, so I haven't really done anything crazy here. I know that the physics is going to come from my radial equation, and now I'm going to start massaging it, which I've done, to get it into this really nice manageable form. Rho naught is defined by all these constants, but it's okay. We'll worry about it at the end. Okay, excellent. So I'm going to rewrite my rho equation up top, and let's solve it. And you're going to learn some really important mathematical techniques now, which you will use your whole life if you go into physics, especially. But even if you go into other fields, math, engineering, you'll use similar techniques. Okay, so now I have my substituted equation, my radial equation, which looks very different than when we started, but it's not really different. I just made some really nifty switches. Okay, so now, the way you solve this thing is you use this mathematical technique called asymptotic forms. So what do I mean by that? All I mean is that we are going to analyze this equation in certain limits. Okay, we have a lot more to do. I think we'll be able to finish today. If not, we'll wrap up next time. This is really the big calculation of this class, other than perturbation theory. So, in some ways, this is the most important calculation in this class. Okay, so we're going to do this thing called asymptotic forms. We're going to look at, so all that means is, you guys know what limits are from calculus. I'm just going to look at particular limits of this equation to try and solve it. And the reason I can do that is because if I look at particular limits, I'm going to get good approximations to this. So we can't really solve this explicitly, but that's not so important. We want to try and get really close to the solution by looking at the asymptotic forms, by taking certain limits. So the first thing I'm going to do is let's look at this thing as rho goes to infinity. So as rho goes to infinity, this equation becomes d2u over d rho squared equals u, right? Because this is going to become really, really small and overtake these terms, right? Because this is rho squared. The 1 will stay there because it's 1 plus a really tiny number, and I'm just going to have a u. Is anyone confused about how I did that limit? I'm going to do a lot of them now, and I'm not going to explain them if you guys feel okay with it. Mansoor, Ariam, are you guys, is that okay? Have you done those kinds of limits before?
Not really.
Okay, so I can explain it, no problem. So what am I saying here, Mansoor? I'm saying I'm going to let rho get really, really big, right? So what's going to happen as rho gets really, really big? As rho gets really, really big, this is going to become a small number, right? Because this denominator is going to get small, right, Mansoor?
Mm-hmm.
This denominator is going to get even smaller because it's rho squared, right?
Yeah.
So this whole piece, rho naught over rho plus L times L plus 1 over rho squared, this is kind of just 0 because it's such a tiny number that in the limit, as it's going to get even bigger and bigger and bigger. This is going to get closer and closer to 0. So this term I can just ignore. And all I'm left with is 1 times u. So I have a u remaining.
I get it now.
Okay, yeah, so that's what I mean by taking a limit. And in a sense, it's an approximation, right? It's an approximation. Because it's not an exact thing, but we're trying to approximate it, to simplify it, and we're going to get a good result. Because even if we're off by like 0.000000001, who cares, right? So that's what I did here. Obviously, nothing happens to this term because this is a derivative. So this is not the same thing as saying, oh, rho is getting really small or really big or whatever. Okay, is that clear?
Yeah.
Okay, so now this equation has general solutions. U of rho equals AE to the minus rho plus BE rho, which are the kinds of things we've been seeing. Okay, and now we have the same game. E to the rho is going to blow up, so it blows up as rho goes to infinity, right? Because as this keeps getting bigger, this exponential is going to blow up. And we can't have that because we want this thing to be able to be normalized. So we have to set B equal to 0. Okay, and we get our final result that U of rho is approximately, because again, we're taking a limit here, equal to AE to the minus rho. Okay? For large rho, we should probably write that. For large rho. This exponential is not going to blow up as rho goes to infinity because of the minus sign. This one will. Similarly, as rho goes to 0, right? As rho goes to 0, the centrifugal term dominates, right? So you can work out that limit in your head. Okay, so as rho goes to 0, my equation becomes this. D2U d rho squared equals L over L plus 1 over rho squared U. Now, how did I get that? So rho is going to keep getting really, really small. Let's work this out once. So rho is going really small now, right? Before rho is getting really big. Now rho is getting really small, right?
Mm-hmm.
So what happens to this fraction as my denominator keeps getting smaller and smaller?
Then the number gets bigger.
Gets bigger and bigger. So this term is going to get bigger and bigger. This term is also going to get bigger and bigger. But since this is rho squared, this term is going to get bigger faster than this term. So this term is going to be more important, right?
Mm-hmm. Mm-hmm.
Yeah. So that's why my equation simplifies to this. This should be a d rho squared. And the centrifugal term dominates in that limit. Very important to remember, though, as we're doing this, that rho is some number. It's a bunch of constants. So rho is important. It's not some random thing. I defined it very particularly. Okay, now what we want to do is we want to keep kind of playing around with this thing. So again, this has solutions, right? Okay, so these are the solutions to this thing. And again, rho of minus L is going to blow up as rho goes to 0, and so D has to equal 0. Okay. And we get our final asymptotic solution, which is this, right? Because only the first term survives. This term is gone for small rho. Okay, so now we have two solutions for large rho and for small rho. Okay, now we can do something really nice. Now we can introduce another function. Well, we can't really introduce another function. Now what we can do is kind of interesting. We can write down our solutions for our big equation as a sum, as a multiplicative sum of the two solutions from our asymptotic behavior. So I'll show you how that works. And that's why we did this whole process. And what we're getting is a nice approximate solution. Okay. Okay, so we have our asymptotic behavior that we've just analyzed, which is not so complicated once you just kind of think about it a little bit. If you haven't seen a limit, then it's going to be a little complicated. So we introduce this, V of rho, okay, and I define it in the following way. So U of rho is equal to rho L plus 1 e to the minus rho V of rho. Okay, so I've taken my asymptotic solutions and I've defined a new equation in the hopes that if I put this thing back in, this function, it's going to simplify my equation because I know these are solutions in certain limits. Okay, so now what happens to my, well, let's differentiate this first. So let's do du d rho. So we're differentiating this thing. And what we'll get is rho to the L, e to the minus rho, right? Because when you take the derivative, power law, you're subtracting this one. The exponential derivative stays the same. And then I'm going to get some chain rule stuff. Okay, so I've just done du d rho, just differentiating this thing. And this chain rule stuff is going to come from this, right? Okay, let's differentiate it again. Let's take the second derivative. You're going to get this mess. Plus rho plus L times L plus 1 over rho V plus 2 d rho plus rho. You know, these derivatives get long. Okay, so that's the second derivative. I'll give you a second to copy that. Might go over today for 4 or 5 minutes. Okay, so that's my second. So I've just differentiated these things. And now I can plug it in to my Schrodinger equation, the radial equation. Okay. So I'm not, I want to erase the bottom if you're copying it. And my radial equation becomes this. Okay, so now I have a radial equation. It's written in this kind of form using these rhos and u's and l's. Right? And now we want to find a solution of v of rho. Okay, because we've defined the new function v of rho. And that's what's going to give us our solutions. And we're going to say that the solution is going to come in the form of a power series that looks like this, a power series in rho. So our v of rho is going to look like something like this, some kind of power series with coefficients aj, rho j. Okay, so this is the form of the solution. And now we want to determine the coefficients A0, A1, A2, A3, A4, A5, A6, and so on and so forth. Okay. So let's do the following. So let's differentiate dv d rho, this thing. So if I take this derivative, I get what? I get same sum. Right, and I'm just going to be using the power rule. I'll get a j, a sub j, rho j minus 1. Just equal to this same sum, j plus 1, a, j plus 1, rho j, okay, when I take the derivative. Okay, let's take the second derivative of my power series. And I get j plus 1, a, j plus 1, rho j minus 1, just using the power rule. Now let's do the obvious. Let's plug in our power series into the radial equation, right? Because I have d2v d rho squared, right? And I have dv d rho. That's why I wrote it out as a power series, because I want to plug it back into my radial equation. Does that make sense, guys? Why I did these derivatives?
Yeah.
Yeah, because now I just want to plug them back in. I've said that the solution is going to be a power series. That's just that just came out of thin air. Okay, so now let's rewrite our radial equation again, but now with our power series derivatives, d2v d rho squared and dv d rho. So now the radial equation is going to have these summations in it too. This radial equation looks nasty now, but it's actually going to work out nice. It's 2. All right, and now we're going to have our other derivative. Hop in. Nothing complicated again. We're just subbing in our power series and derivatives of the power series. Nothing crazy. Now I can get rid of the summations and do some manipulations, and this reduces to this thing. It follows pretty easily. If you stare at it for a minute, you'll see how. Okay, now I can do a little bit more algebra and I get this expression for aj plus 1, the coefficient. This is an extremely important mathematical technique. Honestly, okay. Okay, so we have gotten to a very important formula. So we have a few minutes. I think, yeah, we can finish up today. It's okay if I go like 10 minutes over, right? Is that okay?
Yeah.
Okay, because I don't want this to linger. So all I've done is some algebra, but now you can see that I have a formula that's going to determine my coefficients. I have aj, and then I have some next coefficient, aj plus 1. So this is a2, this is a3. And this is so important, you should look up this as a mathematical tool. This is a recursion relation. I'm sure you've heard of them in some context before in a math class. Recursion relation, or recursion formula. So now we've turned our radial equation in this crazy way, looking at asymptotic solutions, looking at power series solutions, expanding it, plugging those in, differentiating each term, and we've gotten what we wanted, which was a recursion relation, which will determine the coefficients, which will determine V of rho, which will help us solve this thing. Excellent. So now let's finish this thing up now, and let's get to the most important equation in quantum mechanics. Which it's okay if you didn't even follow it. Well, for those of you that want to do research, you should know this decently well. Okay, now let's look at another limit. Let's look at the large J limit. Okay, so for large J, or if J goes to infinity, what happens? Again, these approximations make our lives easier. So aj plus 1 goes to what? Aj plus 1 goes to 2j over j plus 1, j plus 1. Aj equals 2 over j plus 1, a sub j. Okay, and then aj goes to 2j over j factorial times some constant, a. Okay, now we can write v of rho in the following way, using these approximations. What did I do here? Basically, I have redefined the Fourier coefficient, right? This is just the power series, right? Rho j stays the same. And what did we do? We found a recursion relation for aj, and I've replugged in that coefficient. Again, this has a solution. U of rho equals a rho L plus 1 E of rho. Okay, so now I'm doing the same kind of game, except we have a problem. At large rho, this thing blows up. So I'm going to erase the recursion relation, which is really what we needed to finish this thing up. We have a problem. Blows up at large rho. So we must have this power series end at a certain point, so this can't blow up. In other words, we can't let rho go totally to infinity. We have to cut it off somewhere. So we'll define some aj max, right? Some maximum Fourier coefficient, so this thing doesn't blow up. And if we add 1 to that j max, we get 0. We've terminated it. So if you even go 1 over that aj max, you're going to get 0. And so now our recursion relation is going to be a little different. It's going to be aj max plus L plus 1 minus rho naught equals 0. Okay. This is our recursion relation now. Coming from, again, the asymptotic behavior. And now I'm going to redefine this thing here. So I'm going to call this thing n. Right, so we'll say n equals j max plus L plus 1. And we're going to, so then this thing reduces to what? Rho naught equals 2n. Okay, and n is called the principal quantum number, or the first state we start at, first energy eigenstate, or the ground state. Okay, but we have a very important thing. Rho naught determines the energy, right? Rho naught is, so basically this n is just some integer, right? This is just going to be some number. I've redefined it in a certain way because this thing will blow up as rho goes to infinity. Okay, and then rho naught is some number. So I've separated these terms here, okay? And now I've come to this final little tiny formula, but rho naught depends on the energy. So we've derived an expression for energy that solves that equation. Okay, so let's write that out. And this is the big triumph of quantum mechanics. And by the way, I'll talk about it once we derive it. So we have rho naught equals 2n. But if we plug in our thing for rho, we get that E equals minus h bar squared kappa squared over 2m, right? But then we also define kappa. So E equals minus m e to the 4th over 8 pi squared epsilon naught squared h bar squared rho naught squared. Okay, and then if we plug in our thing for the recursion relation, we get that E sub n, our energy eigenstates, equal this, minus m over 2h bar squared e squared times 4 pi epsilon naught squared times 1 over n squared equals e1 over n squared and so on, where n is an integer value. And this is the most important equation we'll derive all term, even though we'll learn scatterings and stuff like that. This is the Bohr formula. And this is what can tell you precisely the energy eigenstates of hydrogen if you plug in different values for n. What's even more stunning is that Bohr computed this in 1913. Schrodinger discovered his equation in 1924. That means Bohr discovered this thing before quantum mechanics. Bohr used a very complicated argument, okay, which we did not do here, to derive this beautiful expression. So this is extremely incredible that from quantum mechanics we can derive the exact, and with constants too, so this is an exact number, energy eigenstates for hydrogen. Pretty phenomenal. Okay, let's derive some more excellent quantities. So this is the most huge triumph of quantum mechanics. And I know the math might have been a little abstract, but if you sit with it, you'll get it. And if you do some reading, you'll get it. So let's define kappa, another kappa, as me, I ran out of stuff, me squared over 4 pi epsilon naught h bar squared, 1 over n. Right? And this is just 1 over an. Okay, and now I have to define a. So I define a as 4 pi epsilon naught h bar squared over me squared. This is a number, right? E is the charge and everything. This is equal to 0.529 times 10 to the minus 10, it turns out. Okay, very tiny number. And this actually turns out to be the Bohr radius. Pretty awesome. And what is the Bohr radius? It's that radius between the proton and the electron. It's the distance between the proton and the electron. So isn't that insane that we're able to get this number? I mean, that's crazy. And very precisely, just using our constants, which is a big philosophical mystery. How do these numbers come out from the physical constants? So we have our Bohr radius. Okay, and let's write down some final things. Pretty incredible. You know, but be happy while you can, because this is one of the few real systems we can solve so precisely. Okay, now we're going to have a wave function for hydrogen. So these are our wave functions for hydrogen. They're going to have 3 degrees of freedom, right? R, theta, and phi. Hydrogen. We have R and L, another special polynomial I'll define. Y are spherical harmonics. Y, M, L, and R. Theta and phi. Okay. And where R and L of R equals 1 over R, rho, L plus 1, e to the, so it's that whole asymptotic expression. Okay, and if we want to solve for an energy, let's solve for the ground state. So E sub 1, so this is n equals 1, the energy. We get minus, using our Bohr formula, m over 2h bar squared, e squared over 4 pi epsilon naught squared equals minus 13.6 eV. So this is the units we use, called electron volts. And this turns out to be the binding energy of hydrogen. So the ground state, plugging it into our Bohr formula, is the binding energy. So the binding energy is the energy, the minimum energy required to keep an atom intact. In other words, if the hydrogen atom had less than this amount of energy, your hydrogen atom would collapse. let's just do an E2 for kicks. E2 is minus 3.4 eV, the first excited state. So it's getting more excited, it's getting more energy. Okay, and I have to give you a definition for the normalized hydrogen wave function. So psi NLM equals 2 over NA cubed n minus L minus 1 factorial over 2n n plus L factorial cubed square root. So these are just definitions like spherical harmonics. E to the minus R over NA, except now you have 3 degrees of freedom. 2 times R over NA to the L. Capital L, I'm going to define this, 2L plus 1, n minus L minus 1. So, I mean, this looks complicated, but it's not. You're just picking numbers for N, L, and M and plugging them in. It's not very, very tricky. 2R over NA, but you need these formulas. Y, M, L, the corresponding spherical harmonic. Let me define what L is. So now we have our binding energy, we have our, I can tell you the radius, I can tell you the energy. Binding energy, excited states, and the radius of the atom. So L, this L bit is called a Laguerre polynomial. So we have a lot of special functions now. We could have had more, but I decided not to. 2 R's. Laguerre polynomial. And this is equal to, defined as e to the x d dx q. And you must be like, where is he getting all this stuff from? Mathematicians actually have defined these polynomials to solve particular differential equations. So when you see a differential equation of a certain form, you know what kind of polynomial will solve it. All of these polynomials are orthogonal. And again, our hydrogen wave function is normalized. Sorry, now we integrate over all dimensions, sine theta, dr, d theta, d phi again. Now we get 3 Kronecker deltas, because now we have 3 degrees of freedom. Okay, that's that. I mean, we've gotten the hydrogen energies. We've worked through this long procedure, and we've gotten the binding energy. And we have our wave functions for hydrogen that can tell us really anything about the hydrogen atom. So it's really honest, it's kind of a shame more people weren't here. This procedure is super important. I would go through this a few times because we do similar procedures with differential equations many, many times. Okay? Okay, thank you. So next time we're going to do scattering. We're going to do the S matrix. We're going to see what happens when you collide 2 particles together in quantum mechanical context. I must say, this calculation is like a rite of passage. It's really an important calculation to understand all the steps. You know, and this looks intimidating, but it's really not. It's just sort of building one on top of the other, like a machine. Okay? All right, great, thank you. See you all next week. There'll be a problem set, and I'm really excited to read your papers. I will stop recording and take any questions.